Welcome back to Very Ordinary Differential Equations. In this lecture, we begin studying how to solve linear first-order systems of equations, beginning with the simplest scenario. Now, our starting situation is going to be this. We have a first-order linear homogeneous system with constant coefficients. So in other words, y1 prime is expressed as a linear combination of theyn's plus some forcing function and y2 and so forth, but our simplifying assumptions are that these coefficients aren't functions of t, just constants. Also, the forcing functions are all zero. In this case, I can represent the system as y prime is ay, where A is a matrix with real number entries. Now, for homogeneous linear equations of just one function that had constant coefficients, we found solutions by forming the characteristic polynomial and finding its roots. And the idea here was that e to the lambda t is very easy to work with, and e to the lambda t would be a solution to the differential equation if and only if lambda is a root of the characteristic polynomial. We're going to try essentially the same thing here. We're going to assume that we have a column vector made up of exponential functions that all have the same exponent. So here we have our column vector y. These coefficients might be different, but the exponential functions all have the same exponent. Now, e to the lambda t is a scalar that we can factor out from this column, and using bold x to just represent a column of coefficients x sub I, we have y is a column of constants times e to the lambda t. And linear algebra comes back into the mix. So here we have our matrix A. We have our column vector y, which is a column of constants times e to the lambda t. Now, differentiating y is quite straightforward. In every single entry, we simply get a scalar multiple of lambda. And if we factor the scalar lambda out on the left and the scalar e to the lambda t out on the right, just to preserve the order of some things later on, we end up with a fairly nice looking derivative here for y prime. Also observe that this column vector y satisfies y prime here is simply lambda times the original vector y. And therefore, if it also solves that y prime is equal to the matrix A times y, if y solves our original differential equation, well then, y prime must equal y prime. So ay would have to equal lambda y. So our column vector is a solution to the differential equation if and only if ay is equal to lambda y. Of course, y was just the column vector x e to the lambda t. We can cancel out the non-zero scalar e to the lambda t, and we derive that ax must be lambda x. In other words, x, this column of constants, is an eigenvector of the matrix A with corresponding eigenvalue lambda, and this was all if and only if. So we can state the following. If we're attempting to solve y prime equals ay, where A is an n by n matrix of constants, if x is an eigenvector with eigenvalue lambda, then x e to the lambda t is a solution to the system. If we can therefore find n linearly independent eigenvectors, then we will have found n linearly independent solutions, in other words, a fundamental set of solutions, which pretty much solves the whole problem. Now, this procedure suffices whenever A has n linearly independent eigenvectors, in other words, a basis of eigenvectors. In other words, when the matrix A is diagonalizable. Altogether, to solve y prime equals ay, where A is an n by n matrix of constants, if you can find n linearly independent eigenvectors and call them x1 through xn with corresponding eigenvalues lambda 1 through lambda n, then the columns xi e to the lambda it form a fundamental set of solutions, and therefore any solution must be a linear combination of those columns. So the c1, c2 through cn are arbitrary constants. For our first example, let's solve y prime is this matrix times y. So what we need to do is find eigenvectors of the matrix. So we need to find eigenvalues. So we're going to take the characteristic polynomial, the determinant of A minus lambda I, where I is the appropriately sized identity matrix. Sometimes you may also see this written as lambda I minus A. Now the only difference is up to a plus or minus sign. And since we're only interested in roots of the polynomial, multiplying by -1 does not affect this. So if you're used to computing the determinant of lambda I minus A versus A minus lambda I, it doesn't matter. So A minus lambda I is the matrix given here. To find its determinant, since it's just a 2 by 2, we take the difference of the diagonals. Now this diagonal, if I just take this minus sign and distribute it in here, it makes it look a little nicer. So we get lambda times lambda minus 3 minus 4. That distributes as lambda squared minus 3 lambda minus 4, which itself factors as lambda minus 4 lambda plus 1. So there are, in fact, two eigenvalues, 4 and negative 1. We have two eigenvalues for the matrix of this equation, 4 and negative 1. What we need to do is find an eigenvector for each one. So for lambda 1, we need to solve a times x1. x1 is now a column of constants, is equal to lambda 1 times x1. So here's the matrix A with an unknown column of constants. In our first row, we get 3a plus 4b equals 4a, and in our second row, we get a equals 4p. Now these two equations are the same equation. Observe, if you were to subtract 3a from both sides, this would simply say 4b equals a equals 4b. So while we do have two equations and two unknowns, we are not going to be able to find a unique solution. Any scalar multiple of an eigenvector is also an eigenvector, so there is not a unique solution here. We're only looking for a non-zero solution. Now the second line, a equals 4b, tells us if one of the two numbers is 0, then the other one must be. But an eigenvector cannot be the 0 vector. So a must equal 4b, but they can't both be 0. Therefore, neither one of them can be 0. So we have these two equations, which, as remarked, really are the same equation. They're not allowed to both be 0, and we can scale them arbitrarily. So taking the information that a must equal 4b, I'm just going to pick b equals 1, and therefore a equals 4. So we have found an eigenvector with that corresponding eigenvalue. A equals 4, b equals 1, so the column is 4, 1, and the associated eigenvalue that we just were working with is 4. Now we have to move on to the other eigenvalue of negative 1. So again, we are attempting to solve axi equals lambda I xi, but lambda 2 is negative 1, so here we are. There's our matrix A, and again, we're representing the column x2 of unknowns as simply a and b. In the first row, 3a plus 4b equals negative a, and in the second row, a equals negative b. And once again, these are not two distinct equations. If you subtract 4b to this side and add this a over there, you'll end up with 4a equals negative 4b, which is equivalent to a equals negative b. So again, we do get two equations, but they are not independent. We are not looking for a unique solution here. Instead, we're just trying to find any non-zero solution. So for example, pick a equals 1, and therefore b must equal minus 1. So we have found another eigenvector with this corresponding eigenvalue. So the eigenvector of 1 minus 1 corresponds to the eigenvalue of negative 1. We have a 2 by 2 system that we started with. We have found two linearly independent eigenvectors, so we have found a fundamental set of solutions. Here were the eigenvectors with their corresponding eigenvalues. 4, 1 went with 4, and 1 minus 1 went with minus 1. Therefore, a fundamental set of solutions is given by the column 4, 1 with e to the 4t, and the column 1, negative 1 with e to the minus t. So we have found a fundamental set of solutions, and therefore the general solution is simply linear combinations of them. Now, if you really prefer to represent the solution y as two distinct functions, y1 and y2, well, y1 and y2 are just the two entries of this column. So y1, the top entry, would be 4c1 e to the 4t plus 1c2 e to the minus t. So if you want, you can say y1 must be this here. And similarly, y2, the bottom entry, would be c1 e to the 4t minus c2 e to the minus t. For our second example, let's solve this initial value problem. Well, like always, to solve an initial value problem, we need to find the general solution, and then we will use our initial values. So we represent our system in matrix form. And now we need to find a general solution, so we need to find eigenvectors of that matrix 3, 4, 2, 1. So we compute the characteristic polynomial. If we do lambda I minus a, we get lambda minus 3 minus 4 minus 2 lambda minus 1. So lambda minus 3 times lambda minus 1 minus negative 4 times negative 2. So lambda minus 3, lambda minus 1, minus 8. Distribute this all out, you get lambda squared minus 4 lambda minus 5, which itself factors nicely as lambda minus 5 times lambda plus 1. So there are two eigenvalues, 5 and -1. So we found the eigenvalues of our matrix. Let's take the first one, lambda1 equals 5, and find corresponding eigenvector for it. So we set up the matrix times a column of unknowns is 5 times that column. Now the two rows give us the same information assuming we have found our eigenvalues correctly. So we really only need to work with one of them. So for example, the first row, 3a plus 4b equals 5a. Now subtracting the 3a to the other side gives us 4b must equal 2a. We can't have them both be 0. So if we go ahead and set a equals 2 and b equals 1, that is a possible solution. That gives us the eigenvector 2, 1 with corresponding eigenvalue 5. There is another eigenvalue to work with, however, of -1. So we go ahead and set up the matrix times an unknown column is -1 times that column. And again, the two rows will give us the same information. Therefore, we just pick one of them to work with, 3a plus 4b equals -a in the top row. Manipulate this and you will solve for b equals -a. They can't both be 0, so let's just find any solution we can. How about a equals 1 and b equals -1? Well, that gives us the eigenvector 1, -1 corresponding to eigenvalue -1. So we have found two linearly independent eigenvectors with corresponding eigenvalues, 2, 1 and 1, -1, with eigenvalues 5 and -1 respectively. So a general solution is a linear combination of the column times e2, the eigenvalue times t. Our initial conditions, however, tell us that y of 0 must be 2 and -1. y1 of 0 is 2, y2 of 0 is -1. So y of 0 is the column 2 minus 1. Plugging t equals 0 into exponentials is awfully nice. It simply makes them 1. So here's our initial conditions, which we're going to use to solve for the coefficients c1 and c2. In the first row, we get 2c1 plus c2 must equal 2. And in the second row, we get c1 minus c2 must equal -1. Now observe that the c2s can pretty quickly be canceled here. So if we add the two equations together, we can quickly solve that c1 must be a third. Then in either equation you want, with c1 equals a third, then c2 must equal 4/3. So go back to the general solution and replace the coefficients c1 and c2 with 1/3 and 4/3, and you get y must be 1/3 times the column 2, 1, e to the 5t, plus 4/3 times the column 1, -1, e to the -t. For our third example, let's find a general solution to y prime equals ay, but now A is a 3 by 3 matrix. And we begin by computing the characteristic polynomial. I think it's easiest to expand along the left column due to the presence of these zeros here. So if we simply compute the determinant of a minus lambda I, we just have to subtract lambda along the diagonal. Then the determinant of a minus lambda I would be 6 minus lambda times the determinant of this 2 by 2 matrix, which would be 16 minus lambda times 2 minus lambda minus -5 times 8. 16 minus lambda times 2 minus lambda plus 40. So here is the entire determinant of a minus lambda I. Once you expand everything out, we end up with negative lambda cubed plus 24 lambda squared minus 180 lambda plus 432. It's worth remarking, if instead you computed the determinant of lambda I minus a, then you would have gotten a characteristic polynomial of lambda cubed minus 24 lambda squared plus 180 lambda minus 432, and the roots would be the same. And remember, that's really what we're after here, the roots of the characteristic polynomial. Those will be our eigenvalues. Now, after some work, we can factor this cubic as 12 minus lambda times lambda minus 6 squared. So there are, in fact, only two eigenvalues, 12 and 6. We are, however, hoping for 3 linearly independent eigenvectors. It doesn't mean we don't know what to do. We're going to try doing all the same steps. So our approach requires finding n linearly independent eigenvectors, but remember, they don't have to have distinct eigenvalues. It's possible for the eigenvalue of 6, since it appears with algebraic multiplicity 2, it might have geometric multiplicity 2 as well. There might be 2 linearly independent eigenvectors for the same eigenvalue. So let's begin by working with lambda equals 12. It only had algebraic multiplicity 1. 12 minus lambda only appeared once as a factor of the characteristic polynomial. Therefore, it can have at most and at least a one-dimensional eigenspace. So we're going to find a corresponding eigenvector by solving ax equals 12x. Represent x as a column of unknown constants. Now, if I try to put the column A, B, C next to the matrix A, row by row, it's pretty easy to multiply. Also, 12x is pretty easy to multiply. So in the first row, 6a plus 18b minus 9c equals 12a. Here are the second and third rows, respectively, when you do all that multiplication. The last two equations are equivalent to one another in this example. Observe, if you move the 5c over to this side and subtract 12b, you get 4b is equal to 5c. Similarly, here, if you simply subtract the 2c, you get 8b is equal to 10c, which is just twice what that one did. Either way, we have the information 4b is equal to 5c. So here were our three equations and three unknowns, but the last two are exactly equivalent to each other. Again, you're not looking for a unique solution, you're just looking for any solution. And we already determined that 4b must equal 5c. So let's, for the sake of argument, let b equal 5 and c equal 4. That will satisfy that 4b equals 5c. That will therefore satisfy these two equations automatically because they don't have any a's in them whatsoever. But if we go ahead and take b equals 5 and c equals 4 and plug them in here, you can then solve that a must equal 9. So a corresponding eigenvector is given by 9, 5, 4. And that was for the eigenvalue of 12. Now the other eigenvalue was 6, but it had algebraic multiplicity 2. Lambda minus 6 appeared twice in the factorization of the characteristic polynomial. So the eigenspace is either one-dimensional or two-dimensional. Its geometric multiplicity is either 1 or 2. We really hope it's two-dimensional because we don't know yet how to handle the situation where we can't find n linearly independent eigenvectors. So let's go ahead and set up ax equals 6x. In the first row, second, and third row, here's what you end up with. In the first row, notice that the 6a on the left and the 6a on the right can simply be canceled out. In other words, a is absolutely absent from this system of equations. Canceling the a's from the first equation leaves no a's anywhere else. So we really have three equations in two variables, so we expect lots of solutions here. Once we cancel the a's from both sides of that first equation, here are the three equations we have left. Now from the first equation, we immediately see that c must equal 2b. Once you take the knowledge that c is equal to 2b, both of the other equations are automatically satisfied as well. So the only requirement to solve all three equations simultaneously is that c is equal to 2b. Now a doesn't appear anywhere, so it's free to be any value that we want. So for example, if c is equal to 2b, we might let b equal 1, c equal 2, and for simplicity's sake, just let a equal 0. There is an eigenvector. Or you could let b and c both be 0. Now an eigenvector can't be made up of all zeros, but remember a is free to be anything it wants. b equals 0, c equals 0 does satisfy c equals 2b, and then I let a equal 1. And what's nice about this choice is that these two eigenvectors are obviously linearly independent. Okay, what you could do, however, is you could say b equals 1, c equals 2, a equals 0, or b equals 1, c equals 2, a equals 1. Those would also be two linearly independent eigenvectors. Okay, but we made one particular choice of two linearly independent eigenvectors, and here they were, 1, 0, 0, and 0, 1, 2. These are two linearly independent eigenvectors for the same eigenvalue of 6. Now we already discovered that the eigenvalue 12 had an eigenvector of 9, 5, 4. So we have three linearly independent eigenvectors with their corresponding eigenvalues, so we can write our general solution as some constant times each eigenvector with e to its appropriate eigenvalue times t. Notice both of these terms have e to the 6t. That's fine because this eigenvalue corresponded to two linearly independent eigenvectors. So here is our general solution. Well, overall, what have we done? If you have the first order homogeneous linear system y prime equals ay, where A is an n by n matrix of constants, first consider that matrix A. If you can find n linearly independent eigenvectors x1 through xn with corresponding eigenvalues lambda 1 through lambda n, then a fundamental set of solutions is given by the eigenvectors times e to the eigenvalue times t. Then you can write a general solution as an arbitrary linear combination of those elements of the fundamental set of solutions. What can we do, however, if there are not n linearly independent eigenvectors? In other words, what if the matrix A is not diagonalizable?